A common mistake early engineers make is treating Verilog like C or Python. You are not writing a sequence of instructions for a processor to execute. You are defining the exact physical arrangement of electronic structures on a silicon die. When you feed your code into a synthesis compiler, its entire purpose is to translate abstract text into a literal circuit board of logic gates and registers. This generated Cortis RTL schematic is the physical manifestation of that translation. Notice the distinct physical boundaries the compiler has drawn here. This central yellow block represents the physical memory array that holds the system's state. On the left, we have abstract, behavioral case statements and if-else logic. On the right, those text blocks transform into hardwired OR gates, NOT gates, and flip-flops. But how does the compiler know to map that specific abstract code into this exact physical arrangement of hardware? To answer that, we will examine a standard finite state machine, specifically a simple controller that relies on a single input to transition between states. Mastering Verilog requires you to reverse engineer the compiler's logic. You have to learn how it interprets your syntax into silicon. Advanced RTL design means anticipating the physical netlist long before you type your first line of code. Our behavioral plan for this controller is straightforward. We have a 5-state system driven by input A. Standard binary mathematics tells us that to represent 5 unique states, we need exactly 3 bits of memory. Log base 2 of 5 dictates a 3-bit register. Yet, looking back at our physical schematic, the compiler generated 5 internal registers, indicated by the multiple output lines here. It ignored the mathematical minimum. The reason for this anomaly lies in the exact parameter declarations at the top of the Verilog code. We explicitly defined the states using one-hot encoding. In a one-hot system, exactly 1 bit, 1 physical register, is active at any given moment. The rest remain at 0. The primary disadvantage of this method is the physical space it consumes. It forces the FPGA or ASIC to dedicate more physical flip-flops to the machine than mathematically required. The advantage is that it drastically reduces the number of combinational logic gates required to calculate the next state. The hardware doesn't have to decode a complex binary sequence. It only has to detect a single active wire. Synthesis tools frequently favor this trade-off. Swapping dense logic gates for a few extra registers is a highly effective way to achieve higher maximum clock speeds. The compiler did not make this structural decision independently. It allocated the silicon based strictly on the parameters set by the coder. Defining your state parameters is the first active step in controlling the physical hardware footprint of your design. We achieve predictable synthesis through structural methodology. The cardinal rule of advanced FSM design is strict isolation. State memory must be completely separated from next state logic within your code. We establish this isolation by creating a sequential logic block, triggered exclusively by the rising edge of the system clock. This specific syntax directly translates to the physical state registers, the D flip-flops, in the compiled RTL design. Inside this block, we use non-blocking assignments. This syntax guarantees that all state bits physically update simultaneously the moment the clock pulses. Next, we define a second, entirely separate block, the combinational logic block. Because it lacks a clock trigger, this hardware constantly evaluates incoming signals. Here, we use blocking assignments inside a case statement to map out the transition conditions. This case logic forces the compiler to lay down the physical routing of OR and NOT gates leading into the registers. Failing to separate these blocks is dangerous. If you mix memory and logic or miss a default statement in a single block design, the compiler will panic and infer physical latches to hold the data, severely destabilizing your circuit. Adhering to a strict 2-block coding methodology guarantees that the compiler generates distinct memory and logic pathways, keeping the hardware entirely predictable. The final requirement of our FSM is generating the actual command signals to control the rest of the system. Because our output is tied exclusively to the current state and ignores any live input changes, this architecture functions as a Moore machine. We handle this in a dedicated output logic block, mapping specific command parameters directly to their corresponding states. The synthesis tool translates this assignment block into the final physical signal path leaving the state machine. If we look closely at the right side of the compiled schematic, we can see the results of the compiler's hardware optimization. Certain output bits bypass the logic gates entirely. The compiler recognized that it could optimize the circuit by wiring those specific output lines directly from the state register pins. Isolating output logic in its own specific code block gives the synthesis engine maximum freedom to optimize this final physical routing layer. Now we face a severe physical constraint. What happens if our input A is triggered by a human pushing a button, totally independent of the system clock? We must account for the physical reality of a flip-flop. To register a clean 1 or 0, the incoming signal must be perfectly stable, for a tiny fraction of a second right before and right after the clock ticks. This waveform illustrates that critical vulnerability window, known in hardware engineering as the setup and hold time. If an asynchronous signal transitions directly inside this forbidden interval, the flip-flop fails to lock. The hardware enters a state of metastability. The voltage gets stuck halfway between high and low, yielding an unpredictable logic state that ripples through the system. In a one-hot encoded machine, this is catastrophic. A metastable misread could easily trigger multiple state bits simultaneously, crashing the entire machine. To prevent this hardware failure, we follow a strict Verilog design rule. Never evaluate more than one asynchronous input during a single state transition. The second mitigation rule targets the memory itself. Any transition tied to an asynchronous input must use adjacent binary codes. This makes gray code the standard choice for asynchronous state machines. This comparison shows exactly why. In standard binary, shifting from 3 to 4 requires flipping 3 independent bits simultaneously. Gray code ensures that moving to the next state only ever requires a single physical bit to transition. If that single bit goes metastable, the system either gracefully stays in the old state or moves to the new one, neutralizing the risk of a multi-bit collapse. Mitigating physical edge cases, like metastability, requires you to proactively alter your encoding strategy at the highest levels of your Verilog script. We have traced the exact path from abstract Verilog parameters down to a robust, physically synthesized circuit. Let us examine this complete RTL schematic one final time. If we go back and replace our one-hot parameters with gray code, the compiler will completely rewire the schematic, visually collapsing the 5 registers down to 3. This single coding change shrinks the memory footprint, but forces an increase in the complexity of the combinational logic gates used to drive it. The compiler is not magic. It is simply an engine that strictly executes the architectural strategy dictated by the structure of your code. Verilog is a tool for hardware architecture, not software programming. Junior engineers write Verilog to pass simulations. Advanced engineers write Verilog to control the silicon.